part.
Oh. Just when I say Windows.
Yeah, and I've got you actually over here, so if you want to.
Okay. Okay, so everybody got a handout sheet. Okay. We're going to take a look at Use Mobile Linux tonight, which is a patch for the Linux kernel. Okay. Use Mobile Linux is a port of Linux to Linux. So how you would port Linux to, say, a Spark, an ARM, IA64, it's simply a port to a software system call interface rather than hardware. So rather than actually having a CPU sitting there handling everything, it actually interfaces with the existing Linux system. So when you build a UML kernel, you end up with a Linux binary which you can execute in user space, just like anything else like Top, PS, Apache, all that sort of stuff. Something quite similar to this is IBM's S390 mainframes, which can run Linux on those, although part of the virtualization on those systems is on hardware, so it's technically not the same. But the similar principles apply. They have a system called a hypervisor, which virtualizes the system calls on the Linux system. So you run Linux on top of this virtual machine, which has the actual physical machine underneath. So rather than running one Linux system, we can run 10, 20, 100 Linux systems on one physical machine. And the Linux system that you get with UML is a complete Linux system. It's the full kernel with memory manager, scheduler, kernel modules, file systems, network devices, everything like that. It's not like a botched version of your Linux kernel which will run Linux binaries to a certain extent. Okay, originally UML was written by a guy called Jeff Dyke who lives up in New Hampshire, and it was written simply as a method of securing services. So you run, say, Bind or Apache under UML instead of running it natively on a running system. And one of the big advantages of UML is that you can run any kernel on top of a Linux system. So a lot of people, Alan Cox, the people who write RiseOFS and things like that, they test their systems with UML, because if the system panics, you just have to go /Linux to restart it. You don't have to go alt sysrec whatever to get all this stack trace nonsense and things like that. And since UML runs on top of Linux, there is still actually some element of hardware that is required to run the UML. And so to a certain extent, UML is only i386 operational at the moment, although people are porting it to Win32 and Spark. And I believe somebody else is also trying to port it to IA64. So you can actually end up running a Linux system natively on the Windows box. It wouldn't be using any sort of emulation like VMware does. You actually run any binaries execute natively on that CPU. So, and to sort of prove the stability of UML, it was merged into the 2.5 kernel tree in September, and it's all, well, at the moment it's maintained up to 2.5.44, I think. So, and so the 2.5 kernel now supports 18 different architectures, of which one is software driven and all the rest are hardware driven. So UML is quite a individual in the architectures in there, but the actual kernel the distributed kernel in 2.5 only runs on 386 systems at the moment. And as a sort of bench test for UML, when that was actually merged was a posting on Slashdot, which linked to userlinux.org, which runs on UML in my house. And it received about 10,000 hits in a couple of hours, and it didn't die. So it's actually fairly stable compared to, say, other virtualization platforms. Okay. UML is available for both 2.4 and 2.5, although the active development only runs in 2.4. So any changes are written in 2.4, then ported to 2.5. And separate people work on various portions of UML. We've got people working on block drivers, we've got people working on network devices. Some people work on security aspects, but mainly Jeff Dyke does most of the coding. He wrote all of the internals and all that sort of thing. UML, well, there's actually two modes of, get to the right page, UML operation. Originally, it was written using what's known as a tracing thread, and UML uses a system called ptrace, which is a method for processes to debug other processes. So the tracing thread sat there, and when UML started a process, it attached itself to that one. So all system calls, signals, and so forth were actually sent to this tracing thread. And then the tracing thread nullifies the system call made by the process, and then virtualizes it, and then executes it itself. So rather than actually the process being aware of the underlying system, this tracing thread keeps track of all running processes on the system. And then it captures anything which they do. So if something tries to open a file, the tracing thread will notice that, and then it will stop the process making a system call directly to the host, which is the running system underneath. And then it will make the system call itself. Now, this is pretty slow because the way tracing thread works is that each process has the UML kernel mapped into its address space. So any process which is running on UML, on the host side of things, it has a process address space and a kernel address space. Now, in theory, any process running on UML can then edit the kernel space and break out to the host. So what the tracing thread does is it has a mode of operation called jail, which has memory protection, although in some cases this is pretty slow because basically for every sort of memory access, it has to check it, make sure it's to the right address, and then either allow it or stop it. And the actual virtualization implementation with tracing thread is pretty slow because originally it was assumed that signals were quicker than context switches, which isn't actually the case anymore. So usually we've noticed that tracing thread mode is around about half the speed of a running Linux system, although depending on what you're doing, it can be maybe 1.5 times as slow. The new version of UML runs a system called SCAS, which stands for Separate Kernel Address Space, which has each process has a separate process space and kernel space. And this requires modifications to the host kernel to provide extra ptrace capabilities to the equivalent of the tracing thread. So each process now only has a user space element to it, and there is a separate process which handles everything else. So unlike tracing thread, when something makes a system call, rather than it coming in, nullifying it, switching this process into kernel mode, then it makes a system call. Instead, in this mode, it gets a system call, nullifies it, then makes a system call itself. In both cases, the kernel makes a system call, but in SCAS mode, it's significantly quicker because it doesn't have to switch the actual running process around. So, and in the later releases of UML from probably Monday, instead of having individual processes on the host for each running process within UML, it actually implements a system where it creates empty address spaces within a single process. So if you run 10 processes on a UML, you only have 2 processes rather than 12 as you would with tracing thread. Now, this is kind of more technical how ptrace works. Most people will know ptrace from things like GDB, strace, all that sort of thing, where you can Control-C it and backtrace it and things like that. But it can also be used to edit and change registers within processes, change the stack, all that sort of stuff. So you can basically get a process, stop it, and then change it, and then set it going again. So it's pretty good like that. I think I've covered most of this. In the new mode, the kernel's modified to provide a system called procmm, which when you open that, it basically creates a new process address space without the process. So it's originally with UML, you would have, if you had n CPUs, you would end up with 2 times n CPUs plus the number of running processes. Whereas with the new system, you only end up with 2 times n, which is obviously scales a lot better. So say if you had a 2-processor UML with 40 processors, you only end up with 44. You would originally have 44 processors running on the host, where in a new system you only end up with 4. So in that case, it's significantly improved. Now, UML is still technically a kernel, even though it runs as a process. As far as the host is concerned, it's just a regular process. It can't do anything that any other process can't. It can't get into kernel memory. It can't access things it's not allowed to. It runs as a non-root user ID, so it doesn't have any root privileges. It can't do anything like that. For any process running within UML, as far as it's concerned, there is only one kernel, which is the UML kernel. So it is in effect jailed from the rest of the system. Processes within the UML can only access resources on the host if the UML is actually providing them to it in the form of a network device, a block device, or a console or something like that. The process within the UML can't directly access the UML kernel memory, so it is still a process, even though it's running on top of a kernel, which is a process. It gets pretty complicated. But processes within UML are just the same as processes running on a real system. They're unaware of the fact that it's not actually a physical system running underneath. They don't know anything about hardware. They don't know anything about anything on the host that you don't decide to let through. UML supports 3 main types of devices: storage, terminals and consoles, and those for networking. For storage, UML uses a system called UML block driver, which basically maps anything that is a block device on the host to a block device on UML. So you can have a logical volume from LVM, you can have a disk partition, you can have a whole disk, or you can create just a image file on a disk, format it, and then use that. The UML system doesn't know anything about, well, the UML processors don't know anything about the underlying storage method. So all they see is a UBD device on the system which you can mount, you can change, you can create a file system with an UML on it or whatever. And as the UML kernel runs as a non-root user, it can't set UID, set GID or anything like that. So any file system operation is performed as whatever UID UML runs as. So if you run UML as UID 500, any file system operation to any UBD device is performed as UID 500. There's nothing you can do about that. You can't become root, you can't change your UID or anything like that. But of course, if you have a image file with, say, an X2 file system in it, things will be written using the UID of whoever wrote it on the UML. So if you mount it and then write something as root within the UML, then it will be written as root to that file system with a UID of 0. So when you come back and mount it, everything doesn't come back with a UID of 500. So if you then mounted that file system on the host over the loopback device, it would appear as being owned by root, even though it's not. UML supports 2 types of terminals, those which are regular consoles and those which are serial devices, although from a host point of view they're both the same. You can attach something like Getty, mgetty or whatever to any of those, so you can have a terminal listen on the UML. And then you can attach various things to the host side of the terminals. So you can attach it to STD in, STD out, anything like that. You can attach it to xterms, to a PTY or PTS, and then attach to it with screen. It also has a system called port helper, which is used for various things, but mainly for running xterms, eterms, or XVT, anything like that. Or you can attach it to a TCP port, so you just telnet to it, and you end up with a console display. UML has a number of different networking drivers to interface with the host. Some of these are actually software driven in that they have actually no interaction with the host, they only run in user space. And the main one of these is UML switch, which is a virtual switch which you attach UMLs to. So you can attach 3, 4, 5, 6, 7, 8, whatever UMLs to it. You can configure them all and they will interact with each other. That communicates over a Unix domain socket, so you don't need root or anything like that. Oops, I'm getting backtracked. There you go. And there's also slip drivers. Multicast requires host support. TimTap is probably the most popular one, and libpcap is a bit different, but we'll get to that later. For block drivers, UML supports a system called copy on write, which means that you can have a image file or partition or logical volume, and you can then come along and use that as a backing store for a cow file, and then any writes you make to that file system will actually be written to a separate file. So this makes it really easy for UMLs to share file systems. So rather than having 10 2-gig files, you make one 2-gig file and then share it between all UMLs. And then anything that those UMLs change in that file will be actually written to a separate file. Now, if you have a 2-gig file and then UML writes a 1K change to it, or whatever the block size is, then that new file will only use 1K on the disk. So this is far more efficient than using lots and lots of separate large files. Or any reading or writing which is made with UML is automatically cached by the host. So if you try and start 20 UMLs, each with a separate 2-gig file, the host will try and pull in 20 2-gig files, and it'll probably go pretty slow. So instead, if you use cow, since most of the system internals are in that one single file, that will be cached. Any subsequent reads will be pulled from the cache rather than from disk. Somebody posted some benchmarks to a mailing list today, and they started 25 UMLs with cow and 25 without. And I think without it took around 10 minutes for them to start up, and with cow it took about 3.5. So it is pretty quick if you've got lots of UMLs. So if you've got 40 UMLs on a system and you have to reboot it, and they all come up when you boot up, then obviously using cow saves a lot of time. If you have a cow file and the original backing file, you can merge them together to make a new file system using a system called UML-move. Interesting name. So you can then continue to cow that file and then use it for other things. Virtual networking, as I said, split into two groups, those which require host support and those which run in user space. The slip and slip drivers are probably the most basic, which you use a basic slip driver like SL attach or something, and they just provide a virtual networking system over a serial line. Slurp is actually quite useful because that allows your UML to have network access without actually having any root access to the host. So any TCP, UDP, or whatever connection which goes out of the UML, the Slurp service running on the underlying host will actually make the TCP connection out. So it works very similar to IP masquerading. Only problem with Slurp is that as it's not running as root, certain things don't work. So you can't make a connection out of a privileged port, and you can't do things such as ping or traceroute, which require you to create a ICMP packet, which would require raw socket support, which you don't have as not being root. The next networking type is TimTap, which uses a system very similar to the EtherTap driver, originally for 2.2. TimTap is most commonly used via VPN things like vTim and OpenVPN. But the good thing about it is, when you create a tap device, you actually get a proper Ethernet device. You get a Ethernet device with a MAC address. You can shove whatever you like on it. You can do IP, IPX, anything like that. So effectively, you have a whole Ethernet device there. And as far as the host is concerned, this is an Ethernet device too. So you can run things like TCP dump on it. You can attach it to a bridge. You can run it under IP trap, anything like that. So effectively, you end up with the UML having a Ethernet interface with one MAC address. Now, at the other end of that, it has a tap device with another MAC address. So you can simply set up both ends of the tunnel, so to speak, and just route over that. The multicast transport uses the multicast capabilities of the host. So you need a host with multicast support, and you literally just start up the UML, tell it to use multicast for that particular network, and then everything that comes out of that network is broadcasted over multicast. It's not particularly brilliant because in high traffic situations it can go pretty slow. But if you've got a host with multicast support and you just want something quick and it works, then it's there. As I mentioned before, UML switch requires a separate daemon running on the host. And this provides a socket for the UMLs. So you run the switch daemon first, and then you attach all of the UMLs to that. And then UML switch can also be connected to a tap device, just as how you can with UML. So you might have one tap device with a particular IP, which is connected to the UML switch, and then you attach all of your UMLs to that switch, and then route out through the IP on its tap device. libpcap is a little bit different in that it's not actually a real networking device, it's what we call a synthetic networking device. When you compile UML with libpcap support, it builds in the pcap library to attach itself to network interfaces on the host. So you can decide what you want exactly to appear on the Ethernet device on the UML. So if we connect our Ethernet device on the UML to, say, ETH0 on our host, and say we just want TCP packets, then if you run TCP dump on the UML, then you will just see the TCP packets coming in from ETH0 on the host. And you can filter traffic based on priority, you can filter it based on protocol, on service type, all that sort of thing. Anything that libpcap supports, it will work with UML. So you can basically build something like snort or iptraf or TCP dump in a box, and you literally just run UML and it will connect to the various Ethernet devices and off you go, and it will log or whatever. So as far as any services running on the host will not be aware of the fact that this is actually happening. So it's great for monitoring, or you can just stick it on a router or something and nobody will know anything about it. UML also has a system called mconsole, which is a management console which operates over a Unix socket. And this lets us do kernel commands which we would normally do via the keyboard on the host. So we can send it a Control-Alt-Delete request. We can send it a sysrec request. And we can also halt it, which is just the same as typing halt at the command line. Anything that you can do via the keyboard on the host, you can do via mconsole on the UML. Although it does actually have some other advantages. You can stop and start a UML kernel. So you can, via mconsole, you can go up to it and say, whatever, stop. And the UML will just sit there in a loop waiting for more mconsole responses. All the processes won't happen because the schedule is basically stopped. And then you can just go back and start it up again, and everything will continue where it left off. Now that's quite handy if you want to back up a file system on your running UML. So you literally stop it, sync it via sysrec, copy the backing install, and start it up again. So hopefully everything got synced to the disk when you did it via sysrec, and then you start it up again, and basically everything's completely unaware. Now the only problem with this is that if you have a UML which is SMP based, you actually end up with two running processes with separate schedulers. So when you go and stop it, depending on which one you connect it to, you stop one processor and the other one's still going. So that doesn't work at the moment, but we're trying to figure that out. Okay. Also, I'm sorry?
When the hot swap CPU support comes in?
Well, there's a kernel patch for that. I don't know if anybody's actually tried it with UML, but the SMP system doesn't work with SCAS at the moment because of the way it accesses memory, but hopefully it will one day. Okay. Also via mconsole, we can manage UML devices just as we would from the UML command line. So if we decide we want to add a extra swap device or add an extra file system, we can do it via the console. And as far as this is concerned, it just another thing appears out of nowhere. It just literally registers it with the system. So we can add network devices, consoles, serial lines, anything like that. Also via mconsole, we can get information on running UML devices. So if we say we want all of our consoles to go to a PTY, until anything actually uses that PTY, we don't know which actual PTI is running on the host. So using mconsole, we can find out, say if we've got our first console, con1, running, and we don't know which PTY it's on, we just ask it which one it's on, and it'll spit back which PTY it's running on. So you don't have to go and mess around within the UML to actually find out what the UML is doing. Okay. UML is handy for a variety of things. As I mentioned earlier, it's good for kernel debugging. You can you can run a UML kernel and bash it till it breaks and then just start it up again straight away. As the UML is processed, you can run it under GDB, just as you would with anything else. So you run a kernel and it panics, and then you just backtrace it. You don't bother with case and loops or any of that nonsense. You just literally backtrace it, find out which line it broke on, and then go back and fix it. Now, if you break a UML, since it's running a user space and can't bring down a host, you can run 20 UMLs to benchmark a file system, to test a file system. And as each of those fail, only the individual UML will fail. The host will still be sitting there quite happy, banging away. It's also useful for education and training because you can make a UML completely separate to the rest of the network, and you can get a box, stick 20 UMLs on it with Red Hat, and give one UML to each user and say, here you go, they can rm-fr/ it for WCARE, and all they will do is rec their own UML. So then you just go and copy out a new file system for them and off they go. It's also quite useful because you can create virtual networks within UMLs. So if you have 5 UMLs running, you can just go and attach them all into a network. You can play with something like Zebra, you can change routing, you can do whatever you like with it. It won't actually impact on the main host. As UML is basically just a kernel, you can run whichever distribution you like on it. So you can run Gentoo, Debian, Red Hat, SUSE, anything like that. So if you want to try out Debian and you're running Red Hat, you can just go and grab UML, grab a Debian file system, run it, and then you've got your own Debian system running on Red Hat. So if you want to try out, say, a development kernel even, or development distribution, you can just go and download it, run it under UML. If it breaks, all it does is break that actual system rather than the host. UML, since a UML is effectively jailed from the rest of the system, you can attach it to a network and then create a honeypot type affair with it. So you can run, say, bind on it and then wait for people to crack it. And all they can do is break into the UML, and depending on how you've got networking set up, they can't do too much else. They don't know they're running on a UML. They just think they've broken into a box. You can block networking externally. You can have it running through Snort or something, and they're completely unaware. So this is similar to jail on BSD, except that with UML, there's actually no awareness of the fact there's anything else running. So you can go and change the IP address on the UML quite happily. Assuming you don't impact anything else on the network, everything else will still run. Also, with this similar idea, UML is also good for sandboxing. So you can run an instance service such as bind, send mail, anything like that. You can run that on a UML. If it gets broken into, well, it's UML. You just go and delete it and start a new one. So it doesn't really matter. Also, on a similar idea, UML is good for virtual hosting. So you can, instead of say having a bunch of dedicated servers, you can just run UML on one box and give each user a separate box. UML runs basically everything that runs in user space, so you can run any service on it. You can run most file systems and networking programs. So if you get a UML, you can go in and install OpenSSH, bind, QMail, SendMail, Apache, basically anything you like. If you're running Debian, you can just go and apt-get stuff, and it'll all install. Most filing systems work on UML as long as they don't require any architecture-specific stuff. So I think XFS works. JFS probably won't work since it requires a binary kernel module. And most networking things work which aren't actually connected to a physical device. So if you are running a UML, you still have a 10-tap driver there that you can use. You have loopback support. You have traffic shaping. You have quality of service stuff, all that sort of thing. So you can basically do whatever you want with the UML that you would with a host. On a kernel front, anything that anything doesn't require hardware will work with UML. So all file systems will work as long as they don't require host support. Any network device that doesn't require physical hardware, you can run printer drivers on it if it doesn't require a physical parallel port, all that sort of thing. There are actually modules that will allow it to access host resources via I/O ports or via various prop devices, so you can actually run USB devices on UML if it's attached to the physical host. So from a development point of view, if you can run a file system or network protocol or network device under a UML and debug it in user space, then you don't need to come along and debug it on a real host. You can just run it on a UML. And as I said earlier, the people who are writing RiseOFS, they actually use UML to develop their system and to debug it, and they've actually committed all the changes back into UML because they found problems with it. As well as regular things like services and stuff like that, you can also run X clients on it. So if you have an X server running somewhere and you want to run Xterm, you can just go and set the display variable and run Xterm, and it will run it on that remote display. UML doesn't care, it doesn't have a physical X server, so you just got to run it on something else. Instead of, if you want to actually run its own X server, you can use something like XNest, which creates an X display within an X display. But you still actually then have a attachment to a existing X server. Or you can use a thing called Virtual Network Computing, or VNC, which is a system written by AT&T Labs in England, which basically creates a virtual X server which you can connect to over a network service like TCP, or you can connect to it with a Java client in a browser or something like that. So the entire system, X server, X clients, kernel, all that sort of stuff, running in user space, completely unaware of anything else that's going on. As a test of UML, one goal was to make UML run UML. So you, in essence, have two layers of Linux running on each other. So you have UML running on a host, and inside that UML, you have UML running in user space. Now, as you can expect, that's pretty slow, but it works. The SCAS code required host support. So rather than come along and breaking the i386 kernel, the modifications were first made to a UML kernel, and then that UML kernel ran another UML to test it out. So it did work like that, and then the changes to the kernel were then backported to the 386 kernel. Anything which basically checks for hardware will break under UML. Depending on what it is, it might not work, or it might make the kernel panic, or it might just lock everything up. One thing that has problems are distribution installers, because they generally check proc entries for devices, they try to probe things and all that sort of nonsense. On the most part, UML can fake this by changing proc entries to pretend it's got ID devices, pretend it's got various other capabilities. So most people can get something like Red Hat, Debian. I think Gentoo installs in UML, but anything else more complicated than that generally won't install. One problem that most distributions have is that the PCMCIA stuff will actually break UML, so it will just literally hard lock. And this is because it probes for certain IO ports which literally don't exist. So it ends up being in a loop and just generally getting confused. So what you then do is you just have to modify the installer slightly, give it a fake probe program that probes for PCMCIA stuff, and that's how people get Red Hat and Gentoo to install. If you want to access hardware on the host, you actually have to tell the UML how to access it, and we do this with using, as in like network devices. You can do it with UBDs or whatever. You can attach a UBD to a physical partition, to a physical device, and then you can say, if you attach it to a SCSI disk, you can then go and fdisk it, and it'll actually fdisk the physical disk. But you'll then need your host to actually provide permission for whatever UID UML runs as to actually perform that function. And VMware is similar to UML in some respects, but on the most part it's fairly different. UML virtualizes the entire x86 architecture, so as far as any UML kernel running, any kernel running on VMware, whether it's Windows, Linux, BSD, they are completely unaware that they're running on a virtualized system. So while this is good because you can run any operating system under VMware, it's also quite problematic because obviously there's a larger overhead because you're actually virtualizing the whole thing rather than just the system calls. But also the kernel which is running it can't take advantage of the host. If the host is sitting there with all this memory and it wants to optimize itself for the memory there, then the kernel that's running under VMware doesn't know anything about it. With UML, the actual kernel which is running, since it's running as a process and it's not actually virtualized, the kernel knows it's running on a host. So it can access host resources like proc. It could, in theory, dynamically change its memory based on whatever's available on the host and all that sort of thing. This has a significantly lower overhead than VMware. VMware runs at around about 1.8 times the speed of the, well, 1.8 times slower than the host, whereas at the moment UML runs about 1.25 times slower. So it's significantly quicker running UML, although since UML is literally virtualized Linux, you can only run Linux. And at the moment you can only run Linux on Linux, so it's kind of limiting in what you can do. The main thing I focused on with UML is using it for virtual hosting. We can run basically as many Linux systems on one box as we like. So as long as we've got plenty of resources, we can just go out and build a new UML whenever we like. So if we run 20 UMLs on a box and we've got 1 new boxes, we can run nearly 1,000 Linux systems and just throw it all in one rack. So rather than taking up a whole data center with boxes for virtual hosting, we can just, one second, we can, there we go. Okay, sorry, lost my place. We can basically go and make a virtual machine for anybody who wants one. So if a customer came along and said, I want a new system, rather than having to go dig a box out of a storage area and plugging it in and testing it, we just run a new UML and go, there you go. So it's pretty simple like that. Also with UML, some people might want a box with 64 megabytes of RAM and 10 gig hard disk space, for which they'll use like half of it maybe. So if you go and look on the internet and you find out how much 64 megabytes of RAM costs and a 10 gig hard disk, you'll probably find you can't even buy them anymore, much less get a good deal on them. So with UML, you go out and build a really, really big box. It'll throw lots of kit in it and run all the UMLs on that. So you go and buy big hard disks, big amounts of memory, big CPUs, which generally are better value for money. So you can build a box based on good value for money, and then shell it up into whatever you pass on to the customer. Now, the good thing for UML is low-end services like backup MX, backup DNS, all that sort of thing, which generally don't consume much resources. You don't need a 3U box with 100 gig of disk space and half a gig of RAM or something to run that. So you can, if a user wants, they can have a UML with 1 gig of disk space, 32 megs of RAM, and all that sort of thing, running some strange Slackware variant that uses no memory at all. So, in essence, they can have whatever system they like, cut down as much as they like, built up as much as they like, up to the limits of the host. So, rather than saying, if somebody comes along and say, I need a backup DNS server, and you say, well, the cheapest system we have starts at $200 a month, and all I want to do is run backup DNS. With UML, you can instead come along and give them a UML system which basically consumes no resources on your host and charge them $50 a month. So, in essence, it produces a greater flexibility for the customer, because they can basically say, if they want 1 gig of disk space, 2 gig of disk space, 10 gig of disk space, they can come along and decide what they want. They're not physically limited by whatever you have in stock. The problem with virtual hosting with UML is that since you've got 20 UMLs running on one system, if the main system goes down, then all your UMLs go down too. So just as if how you were running a web server on Linux, if that Linux box dies, there's some reason completely unrelated to Apache, then Apache still dies anyway. So you need to ensure that you have a very, very stable host system, because if you've got one host system that has problems and it's used by one user, then okay, it's a bit inconvenient. But if you have one host system used by 100 users and it keeps going down, then they're going to get pretty annoyed. So on the most part, there are various methods to ensure that your host stays stable. Also, compared to running a dedicated server, there are obviously overheads when running UML because of virtualization and because of the way it provides disk access, since it's accessing files, it needs to read the file from the disk and read the actual block of the file system and then all that sort of thing. So rather than reading things directly, there's an extra layer. Also, instead of giving, say, a user a shell or a mail account, you give them a UML box, they end up having to be the system administrator. So half the time you end up with somebody who doesn't know anything about Linux,
with a box, which will probably end up getting cracked and stuff. So you have to ensure that you appropriately educate your users, or otherwise limit what they can do, give them a fancy web front end, or anything like that, just to make things easy for them, because they're not going to take the time to learn how to use Linux if they just want to run a mail server. Generally, you can do anything which doesn't require large amounts of CPU time or anything like that. So it's great for DNS, mail server. I use it for web serving, shell serving. You can run it for basically anything you like. Things like MySQL, Postgre, Oracle probably aren't too appropriate for UML, since they will basically bash the disk, bash the memory, bash the CPU. And in essence, you basically end up with the host spending more time virtualizing everything than actually doing anything. But on the plus side, we can give the users a significant element of flexibility when actually running their system. So rather than having to call tech support every time they want a box rebooted, we can give them a button on a web page, they click on it, and it reboots their UML via mconsole. So all they care about is actually maintaining their UML. They don't have to be responsible for anything else. If we have a new customer come along and say we want UML, we can just roll it out almost straight away based on whatever they want. Assuming we have some preset guidelines as to how much disk space, how much memory, you can just create a shell script that will build all the file systems, install everything, and everything will be up and running pretty quickly. If you want to network a lot of virtual hosts, the best way to do this is with tap devices, because basically a tap device is an Ethernet device. So anything which you do on the host to an Ethernet device, you can do to the tap device. So rather than using UML switch, we can use the bridging capabilities of Linux to bridge all the tap devices into one virtual switch. So we can bridge all the tap devices and the external Ethernet interface on the system. And then all UMLs will route through that external Ethernet device to the network. We can also use the tap devices as firewalls, so we can apply specific firewall options to users. So if we want to block a particular site, block a particular port or something like that, we can do that via the tap device. So rather than blocking on an IP basis on something else, we can block on an interface basis. And as you can see by the picture, since it's an Ethernet device, we can run SNMP on it and then run MRTG or RDD tool over it and get fancy network statistics, so we can easily monitor how much traffic each individual UML is using. So we can ensure that the user doesn't come along and use 100 megabit bandwidth and then blame it on somebody else. The host needs an awful lot of memory. UML creates a physical memory file in the /temp directory. So that could in theory be on disk. But the Linux kernel has a system called tempfs, which originally was called shmfs, since it's basically shared memory between processes, but it's actually memory rather than disk storage. And tempfs is a dynamic RAM disk, so you can make a tempfs system which has a gigabyte of storage, and it will only use whatever you write into it. So if there's nothing in it, then it will use no memory. If you write 200 megabytes into it, it will use 200 megabytes of memory. And as it's a allocated memory storage system, it will be swapped out to disk with everything else. So if you have a 6 gig tempfs system on a box with 1 gig of RAM, then anything over that 1 gig will be written to disk. And if you don't access any of that, then it will be swapped out to disk as well. So by using this method, we can actually give the UMLs more memory than the host has. So if we have a box with 1 gig of RAM, we can give 20 UMLs 128 megabyte of memory each. And then anything they go over 1 gig on the host will just be swapped in and out as needed. So on the most part, you can oversell to an extent. Since UMLs write their files, their memory files into /temp, then your /temp gets consumed pretty quickly, so you have to ensure there's enough space there. And each UML can have its own swap partition, so it's actually more, if you have a UML which is going to use a lot of memory, it's more efficient to give it its own swap partition and then have things swap out to that, rather than expect a host to swap out things from tempfs. because that will then impact on all the other UMLs running on the system. So if you have a UML with a gig of memory compared to one which has 128 megabytes of memory and 800 megabytes of swap, then if you have a tempfs which is 2 gig, then rather than swap out 2 gig of tempfs to disk, it will only swap out 128 meg of tempfs, and then everything else will be written to disk as basic swap storage on UML. UML is generally almost as quick as the host CPU, although the main problem it has is with high I/O stuff like Apache, MySQL, GCC. Basically, if you try and compile a kernel on it, then you will see a lot of disk space. UML disk accesses are cached, so if you compile a kernel and run the kernel compile 3 times, the first time it'll be slow, the next 2 times it'll be pretty quick, because rather than access disk, it will just be pulled from the host cache. And if you have a UML running on a system and then say a user gets naughty and sticks it in a loop, it can then in theory take over the entire CPU of the host. So if you run an SMP UML, so SMP host with lots of UMLs, then you can always have an extra processor. Say if one UML is compiling something, other processors will be scheduled to a different CPU to make it more efficient. On the storage front, if you have a virtual hosting system with UML, and you say want to give each user 2 gigabytes of disk space, if we use DD to make a file system on the disk, we can make a 2 gigabyte sparse file, which will actually take up 2 gigabytes of space in the file system, but on the actual disk it will only take up whatever's used. So say if you make a X2 file system on a 2 gigabyte sparse file, then on the actual disk it may only take up 10, 20 megabytes depending on how you build the superblock. So you can go and make, on a 10 gig disk, you could go and make 20, 100 gig file systems and then build X2 on them, and they'll maybe only use 100 mega disk space. And then from there we can use cows, so if we have 20 UMLs, each running Debian, we can have a single file system and then use cow to split those up, as I mentioned earlier. On the kernel front with the host, the main problem with UML is because it's so memory intensive that when you try and do a lot of swap activity, the host kernel will basically just give up the ghost and die. And I personally experienced many failures of the main kernel system with maybe 20, 30 UMLs running for a few days. So with newer versions of the kernel, and you can apply patches like RMAP and things like that, it will generally work a lot better than if you just run a basic 2.4.19 kernel on the host. And you can apply patches to the host kernel to optimize the scheduling of the UMLs. And say if you have 20 UMLs running, you will effectively only have 20 processes running, even if each UML has 100 processes of its own, because each UML process is scheduled by the internal UML kernel, not the host kernel. So your basic idea is to reduce the latency between the actual UML kernels as opposed to the whole process system on the host. So using something like low latency in the preemptive patch makes it switch between the UML kernels much quicker. And we can also use a system called Fair Scheduler, which stops a single user taking over the whole CPU on the host, as it will basically lower the priority of high CPU operations by a particular user. Now, there's mainly two main groups who are doing virtual hosting with UML. There's my own, which they runs some commercial hosting services, but it mainly runs virtual hosting systems. So I got all my mail, got all my web serving, DNS, and stick it on separate UMLs. So you can then have a separate UML for web hosting, separate UML for DNS, and from a security standpoint, that's quite a good choice. I also provide UMLs to a number of users. So if they, rather than just giving them a shell, and then me having to do all the hard work, setting up their web space, setting up DNS records, setting up mail, I can just say, here's your UML, install whatever you want, and then get on with it. So it's from a administrative point of view, assuming the user is capable of actually administrating the system, then it can be quite advantageous for them to actually run it on their own rather than having to pass requests on to somebody else. I also run UML over a number of hosts, so rather than just having one box sitting there with loads of UMLs, I can put different UMLs on different machines depending on how much CPU, how much disk space, how much memory it's going to use. And because I'm running so many UMLs, I ended up writing a system called UMLD, which is a UML management system, which operates over TCP, which lets myself and other, say if you have a UML, you can then administrate your UML via that rather than actually having to shell into the host. There is also a UML system running by a friend of the original developer of UML who wanted to replace a co-located server, and rather I think he had 21 users, and rather than giving them each a shell, he decided to give them each their own UML. And what actually happened was that everyone gave some money to buy a box. They co-located it somewhere, and then it ended up with its own UMLs running on it. So if you gave him some money, then you would actually have a UML on that system, so you can install anything you like. Each UML on his system has its own IP address, so you can run Apache, you can run anything like that on it with external connectivity. My own system runs around 30 UMLs across 3 hosts at the moment, and I have UMLs for web, mail, and DNS, all of which are accessible via SSH or whatever to regular users, and then as far as they are concerned, it's just a regular box. I can limit the amount of memory, I can give my web server more memory, or whatever, depending on what exactly it's doing. I also host some production level services, including User Mode Linux, which is the main sort of community page for User Mode Linux, which it doesn't get that many hits, but it gets a decent amount of traffic, and especially when it's linked up something like kernel traffic or LWN, it gets a decent beating. So it's actually used for real world things rather than just as a toy. I've also implemented web-based system management via UMLD because I'd originally written a virtual hosting system to manage basically everything, and with a fancy web front end, so people could add virtual hosts, so you could add mail domains and all that sort of thing. So I then added in UML so they can reboot their UML where they click of a mouse, they can stop it, they can start it, they can, if they want to back it up, they can click on something and it backs it up. And the main focus of the hosting system was on scalability and security, so that not only could users not impact my own network, they could not impact any external thing. So I've set up traffic filtering and things like that, and I've also made sure that through kernel tuning on the host that no individual user can bring down the entire host by running like 10 copies of GCC or something. UMLD is a service which runs on any individual host which is running UMLs, and it uses a MySQL backend to store all the UML configuration. So rather than having a shell script to start up UMLs, you run it through UMLD, and it will start it up with all the options it needs. It will set up networking correctly. It will bring up basically anything else that's required for the kernel. And it also has an mconsole interface, so you can basically do anything you do via mconsole via the UMLD. Although UMLD can provide some kind of abstraction to that. So if you want to back up the UML, you just tell UMLD to back it up, and it will stop it, sync it, back it up, start it, rather than actually having to do each one of those as a separate task. With UMLD, it also supports building a new UMLs. Because everything networking-wise is stored in a database, we can easily pick out a new IP address, we can pick out a host name based on whatever we tell it to use. And although at the moment I only use Debian and Woody to build file systems, I can, if somebody asks me, I want a UML, I have a little shell script, I run it, it connects to UMLD, it authenticates me, builds a new one. I can get a new UML up and running in around about 30 seconds. I think the record was about 27 seconds. So based upon how quickly I've been in some shops and having transactions made with credit cards, I figure you can probably build a UML quicker than you can authenticate a credit card. Everything with UMLD is automatic, so if you have a network, you say, I want a network which is, say, a /24/25, it will automatically set up bridging, it will automatically set up a gateway IP address, it will set up routing and things like that. It also supports IPv6, so if you have a /48 routed to your box, each UML will get their own /64 routed directly to it. So they don't need to use any sort of routing system like Freenet 6 or anything like that. UMLD has a very simple protocol which looks and works very similar to SMTP. So you basically send it a command and then you get a numeric response which then changes what else you get back. You can basically write any client you like for it because it runs over TCP, it has a simple protocol, and any user on the system can authenticate with it, and they can then go and access their UML. They can reboot their UML, but only their UML, and then we can set up privileges based on which user connects, and then they can either have root privileges, they can have regular user privileges, they can have restricted privileges, so they can make new UMLs, but they can't actually change anything that's already there. From a remote access point of view, UMLD is useful because we can run it under something like SSL or S-tunnel, so everything running over is encrypted. And also supports CRAM authentication, so it's reasonably secure, although it's open to debate how secure that is. The main advantage of this is that if you give a user a UMLD client, they can admin their whole UML from a host point of view without having a shell on the host. So we can set all the users' shells to bin false, so they can't shell into it, and then they can access whatever we want them to access via UMLD. So we can say if we don't want people to reboot their UMLs, we can stop it with UMLD. And network admins can basically have root access on UMLD via authentication or whatever else you decide to use like that. So they can build new UMLs. They can then bring down UMLs for users. They can back up UMLs and things like that. And at the moment, UMLD only works via a web interface, but at the moment there are console and GDK plus interfaces in development. So in theory, you could have a Perl GDK client running, which connects to a UMLD running on say my host, and you can reboot your UML with a click of a mouse. So from a administration standpoint, that's much better than paying $25 for some guy in a data center to hit the reset button. UMLD is also, since I've run UMLs on more than one host, the main focus of it was to allow me to access the whole network via one connection. So UMLD will automatically figure out which host I'm trying to do something on. So if I decide to reboot the UML on another box, it will proxy a UMLD connection to another UMLD and then run it. So it's completely seamless. So you just have to have one open port on your network. Users connect to it, and everything will be filtered through the network as needed. UML is currently it's fairly development at the moment, and the main change at the moment was the SCAS patches which were implemented in the last few months, and in the last week or so, the UML has reduced itself from however many processors are running on the UML plus 2 times however many CPUs to basically 2 processors per CPU. So if you have 20 UMLs running, you then only have 40 processors rather than maybe 500, 600, 700, which is obviously much better from a host standpoint, plus it gives a bit more speed. People are porting UML to Spark 64 and Win32 at the moment, and Win32 works to a point. At the moment, threads don't work, but you can basically start Bash, you can run X clients, you can basically run anything that just needs clone VM. So I think networking works too, so you could in theory run a very simple web server under Linux on Windows. And Spark 64 is basically in development stages. UML clustering is also in development as well. UML has a system called, it can use a system called OpenMosix, which is a clustering system. So in theory, you could then cluster UMLs across hosts. But from a UML point of view, it's obviously much better to distribute one UML over more than one host. So in theory, the next idea is to allow some variety of host abstraction for UML, so you can run one UML over, say, 5, 6, 7 machines to provide some sort of virtual clustering.
How to make your one machine look like multiple machines, and then make those multiple machines look like one machine.
Exactly. There's some theory to it. As UML is a binary, you can also build it as a shared library. So in theory, you could then You could then build Apache with, say, with Linux, and then you run it, and it will run within Linux. So as far as any running process will actually run within UML, giving it some variety of memory protection, giving it limited access to things on the host, like that. Also, from the point of view of the host, synthetic file systems can be implemented. The main one at the moment is hostfs, which literally allows you to mount a directory on the host within UML and then access it right to a read from it or whatever. So in theory, you could connect it to, say, a web server and browse, say, a web dev directory via UML, or you could connect it to a SQL server, and then rather than doing ls, you do ls select star from blah blah blah. And it would, rather than giving a file list, it would give a row and column list back. So it would give a sort of abstraction level to your server. Using the shared library, you can implement capabilities from other processes. So from Apache, each request could appear as a process within UML. If you want to stop a Apache request, you kill 9 it and it will die. And then something like mod Perl, you could write a script in UML which is connected to Apache in mod Perl, and it will run within the web server. Just as how Perl scripts within mod Perl do at the moment. And then you can then further abstract host resources with UML, so you can then provide access to basically anything which exists on the host as a